Hello and welcome back. We're going to continue our discussion with the 2014 AP exam. We're going to start looking at question number 4. Again, this is the non-calculator section, so this is a no calculator question right here. And it gives us a table, so right away I'm thinking Riemann sums are trapezoid, so let's see if they pop up in here. And it says train A runs back and forth on an east-west section of railroad track. The velocity of train A, measured in meters per minute, is given by the differentiable function. They're going to tell us that. That might come in handy later on today, where t is measured in minutes. So remember that this is a velocity. I always like to identify that, such a velocity. Selected values for the velocity are given above. So the first question says how we want to find the average acceleration of train A between 2 and 8 minutes. So let's see, we're looking for acceleration. Well, we should remember how to get acceleration. That's your change in velocity over your change in time. So this is really kind of like our average rate of change question. So we're looking at our velocity at 8 minus the velocity at 2 over 8 minus 2. The velocity at 8, if I write that out, is negative 120 minus the velocity at 2, which is 100. Interesting. Now, remember, what does that negative velocity mean? Well, we're kind of backing it up, or we're going in the opposite direction here. So that's what that negative velocity there, over 6, and this becomes negative 220 over 6. And you can leave it like this, or you can reduce it to negative 110 over 3. It's non-calculated, don't put a decimal. And let's look at the units. Remember the top, this is in meters per minute, and the bottom is in minutes. So this is going to be meters per minute squared right here. And this is not worth much. It's only worth 1 point right there. It should take you about a minute to answer something like this. All right, question number 2. I love the phrasing here. Do the data. I don't know if that's... Do the data in the table support the conclusion? So anytime they say support a conclusion, somebody's making a statement right here. We want to see if it's going to be true or false. Does the data in the table support the conclusion that train A's velocity is negative 100 meters at some point between 5 and 8? And this should be pretty easy, right? Between 5 and 8, should the velocity equal negative 100? And the answer is absolutely. We're going from 40 to a negative 120. At some point, we have to cross negative 100. So it's easy to know that, but remember, we have to give a reason a mathematical reason. So I'm thinking IVT, the intermediate value theorem right here. So what does the IVT say? Well, the function must be continuous and differentiable, right? So it must be a continuous function. And we do have that. So they tell us the function is differentiable. So we're going to put a nice little phrase right here. Differentiability implies continuity. That's an old statement from earlier this year. Implies continuity. And you can just write it this way if you want. This is the implied statement right there, mathematics. So we're saying that the function is continuous on the interval. So we know that the function, that v of t, is continuous on the interval 5 to 8. And we also know that the value at, that the value at 5, or I should say v of 5, v of 5 does not equal v of 8. They don't. 5 is 40, 8 is negative 120. And the value at 5 and at 1 and that and that negative 100 is between negative 120 and 40. Therefore, we can say somewhere on the interval 5 to 8, the velocity must equal negative 100 meters per minute by the IVT. Something along this line. Now you do kind of have to mention that differentiability implies continuity. Then we're going to use it. Well, since my function is continuous and my values at 5 do not equal 8, and that negative 100 is between negative 120 and 40, we know that somewhere our function must have a value of negative 100 meters per minute. This is worth 3 points right here. Let's take a look at where they come from. Given the position statements, yeah, this is +1 right here. See, the position statements are, we're 2 points. So showing that, and then your answer using IVT is worth another point. So only 2 points, not 3 points. All right, part C. At time t equals 2, train A's position is 300 meters east of origin station. So we're to the east of origin station right here. And the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from origin station at t equals 12. Okay, this is our FTC statement. If I'm given the velocity, I'm looking for position right here. And I know the position at t equals 2. So they're giving me some sort of initial condition right there, and I want to find the value at 12. So as an integral, it would look like this. If I integrate it from 2 to 12 of my velocity, that's going to equal the position s of 12 minus s of 2. Typically, I'll use an f, but this is okay too. So we wrote our integral. That's what they wanted us to do. Write an expression involving an integral that gives a position in meters from the station at t equals 12. And there's our expression right there. And they're going to give you a point for this, by the way, just for writing that out, even if you don't know what to do next. Next, they say, use a trapezoidal, there it is, a trapezoidal sum of 3 subintervals to approximate the position at t equals 12. So now I'm going to go up here, I'm going to use my trapezoid, okay? From 2 to 12, there's going to be 1, 2, 3. So I'm only looking at the region from 2 to 12 right here. So I'm going to go and set that up. So I am going to go from 2 to 12. That was 2, 5, 8, and 12. And my values at 2 are going to be 100, 40, negative 120, negative 150. So here we go. At 2 it was 100. At 5 it was at 40. So there's one trapezoid. And then at 8 it was at negative 120. There we go right here. And at 12, negative 150, right? And there we have it like this. Okay, so we want to find the areas here. So that's what I'm going to go ahead and do here. This is going to give me my areas. And they're trapezoids. So the first one, 1/2. The base is 3. And times the 2 heights, 100 plus 40 plus 1/2. This one has a base of 3. And it's just going to be negative 120 there. So, oops, sorry, it actually kind of measures like this. That's my trapezoid. It's kind of weird. There we go. So it's 40 plus negative 120. And my last one, 1/2, it has a base of 4. And we have the height, negative 120 plus a negative 150 right here. And if you clean all of this up, you're going to get negative 450. You can clean all that up. So what we wind up with is this negative 450 equals s of 12, my position at 12, minus my position at 2, which we know is 300. Therefore, the position at 12 is going to be at negative 150. Now remember, we're traveling east, but remember, east is positive. So I'm at negative 150, so where is this train at? 150 miles to the west. So we can say the train is 150 miles, or sorry, not miles, but meters to the west of origin station. And there, never box in your answers. We're not going to box those in. And there we have it. So we already got 1 point for setting up our integral, you're going to get 1 point for your trapezoid rule, and you get 1 point for your final answer right there. All right, next, lastly, train B. A second train, train B, is traveling north from origin station. At the time t, the velocity is given by negative 5t squared plus 60t plus 25. At time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute, the distance which train A and B are moving at t equals 2. So we're looking for a train t equals 2. So we're going to kind of need this information up here for part C. But again, if you miss part C, don't stress it. Just make up something if you like. All right, so here we go. Actually, at t equals 2, we do know that. So here we go. Here's origin station. So I'm going to set this up. Train B is 400 meters north. So here's train B. It's at a distance 400 meters. Train A, remember, is 300 meters east of origin station. Oops. So if I'm good, this is going to be a right triangle, so I already know that this distance is going to be 500. That's a 3, 4, 5 right triangle. So now we are told that train B, the velocity of train B is given by v of t equals this equation. And we already know the velocity of train A. Now, since we're looking for the rate at which the distances between them is moving, so we got this A, B, and of course we call this C, so we call this distance C. So we're trying to find how dc dt changes. And if you guess this is a related rate, you are correct. So we have to need some information. Let's take a look at anything we are given. We already have the positions, but what about the train itself? dA dt. Well, how fast is train A moving at 2 seconds? I can get that by plugging it going up here at 2 seconds. We know that that's 100. What about train B? Well, train B is a little bit different. We have to plug that in. That's going to be v of 2, and we plug that in. That's negative 5 times 4 right here, plus 60 times 4 plus 25, and what we wind up with is 125. So this is our related rate. I'm kind of running out of room there. So what type of triangle does this fit? Obviously a right triangle. So this can go a squared plus b squared equals c squared. Taking the derivatives, 2a dA dt plus 2b dB dt equals 2c dC dt. And the 2's are all going to cancel. We don't have to worry about those. And I can just plug everything in. A, we know, is 300 times 100. B, we know, is 400. And B's rate of change is 125 if we simplify this velocity. And that's going to equal 500 dC dt. And if I solve for dC dt, we would get the following. And you would solve this and you would get something like crazy number. Don't ever simplify. 300 times 100 plus 400 times 125 over 500, and that's going to be meters per minute right there. Don't ever simplify that. Just leave it alone. And if you do, that's like 160, I think it is. So let's think about how many points this is. All right. Plus 2 for taking the derivative, and plus 1 for your answer. But you got to show your work, okay? You always want to show your work on these. All right, hope you enjoyed the video. Go to the next one, and we'll take a look at video problem number 5. I'll see you then.